Hello, Internet. We are live.
Everyone, welcome to episode 40 of the Stanford MLSys seminar series. I'm Curran, and we have with us, as always, Dan, Fyodor, Piero, and our guests for today, Dennis, Shasha, and Mustafa Kocak. So, as always, we're going to have a 30-minute talk followed by a 30-minute podcast-style discussion where you, in the YouTube live chat, can ask questions and talk to the speakers. A little bit about the speakers. Dennis Shasha is a Julius Silver Professor of Computer Science at the Kumar Institute of NYU and Associate Director of NYU Wireless. He works on meta algorithms for machine learning, one of which we'll talk about today called SafePredict. And Mustafa Kocak is a computational biologist in the Broad Institute of MIT and Harvard, and his interests include machine learning applications, information theory, and biostatistics. This is also the first talk we've had where we have two guests, so it's going to be exciting to see how that works. You folks can take it away.
Okay, great. So you can hear me well, yes?
Yeah, perfectly.
Okay, super. Okay, so this work is Anil's PhD thesis, and I co-advised this work with Elsa Erkip, who's there below, and David Ramirez was also working on the project. So Anil deserves 90% of the credit. All I get is credit for asking dumb questions. Then we have some newer work that we're working on with other people, and we'll discuss that towards the end. So this is a machine learning seminar, so you know that machine learnings are important, but very often predictions can be wrong. Just as people can make bad predictions, so can machine learning systems. And you don't want to make bad predictions. Sometimes you'd rather not act on a prediction rather than act on a prediction you think might be bad. So judicial decision-making, healthcare, for example, you get a test with a prostate-specific antigen and it looks high, you definitely want to check more. So same thing happens with machine learning. You may or may not, as a human, you may or may not believe the prediction. And if you don't believe the prediction, maybe you want to check further, give more data, check the data, do something. So the basic idea of SafePredict is to be a meta algorithm. So it's an algorithm riding on top of a prediction algorithm that will take predictions from the underlying machine learning algorithms. And there could be several of them, and there could be some ensemble method to collect all those predictions and present the resulting prediction to this meta algorithm SafePredict, and SafePredict will decide whether or not to act on that prediction. And acting in our case means not refusing. So SafePredict as an algorithm, as a meta algorithm, can say, no, I refuse that prediction. I'm not going to bother with it. And if it accepts it, then it says, okay, here's my prediction. And of course, that prediction can still be correct or incorrect. And our goal is to have a robust correctness guarantee of some form, like we don't make more than 10% errors or 15% errors on the non-refused predictions. So that's what SafePredict is going to try to do. So why might you refuse? Well, you might refuse because you think, okay, I need more tests. Maybe I need a human expert. Daniel Kahneman, in his book Noise, talks about how really machine learning can be much better than people in many cases, but there are going to be edge cases where people really should get involved. So it would be really nice to have an algorithm that could say, oh, well, I'm really not sure here, I shouldn't do the prediction, then maybe refer to a human. But we don't want to refuse too often, obviously. We don't want to say, oh, well, everything is going to go to some other authority or require more work. So we want to refuse seldom, but we still want to achieve the user-desired error bounds. So just to give you a teaser of what this could look like, so consider an application where the base predictor is, for a while, making very few errors. So our desired error bound is 10%. It's making fewer errors. And then the base predictor goes up and makes 20% errors. and then makes few errors, and then 20%, and then few errors. And what we would like is we would like SafePredict to basically not predict in this region where it's, actually, I'm not sure whether you can see my cursor. Can you see my cursor?
Yeah, we can.
Okay, so we don't want it to predict in the regions where the base predictor is not doing well, and we want it to predict in these other regions. And so what SafePredict, but the point is we want to be within this 10% bound. And what SafePredict will do is, in fact, it will predict, so it won't refuse. So the probability of refusal will go to 0. And then when things get bad, it'll go up, and then it'll come back, not quite as fast as the algorithm, even though the algorithm gets better very sharply, this won't be quite as sharp, but it will get back to not refusing. In other words, probability of refusal of 0, and then it will go up again when the base predictor is bad. So I'm going to give you a very abbreviated literature review, because first of all, literature review could take some time, and also this is an ongoing field of active research, and so there's a lot of wonderful work that's out there also. So the source of this is a nice paper from 1970, which says, well, if I want an error rate of k, so I want to be correct 1 minus k over the time, then I want it to be the case that if my prediction is going to be is y star, say, well, if given an input x, y star, the conditional probability of y star given that x has some value is greater than 1 minus k, well, then accept that, which basically says if you have a high likelihood of getting the right answer, then accept that. The trouble is we don't normally know this probability, but it kind of is a good baseline from which to work. And so when this distribution of correctness is unknown, then there's a wonderful work that tries to estimate when we should in fact accept. And this is for a case where there's where we're looking at a bulk, not an online, but a bulk problem where we are looking at all the data together. In the online setting, we might have a bunch of inputs, x1 through xt, where t is a time, and we have a bunch of outputs so far where we know what the result was, and now we want to say, should we predict the base predictor predicts some yt hat, and should we predict that? And if we do, then we might suffer a loss, which might be, for example, 0 or 1, 0 meaning we got the correct value, so yt equals yt hat, and 1 meaning that we didn't. And what we'd like to do is we'd like to make this put this in an adversarial setting where the adversary can decide how the data input to output is going to go, but does not know the details of what SafePredict is going to do, because SafePredict is going to roll a die and is going to decide based on some randomness. The adversary doesn't get to see that. Now, we're going to, in general, have a set of predictors and maybe use some kind of ensemble method. And then we're going to see that a non-prediction, meaning a refusal, will be basically treated as if it were another predictor. So if there are a bunch of predictors, there's been a bunch of work that says, can I find a good predictor? And so there's work that says, I want to find one of the predictors that's as good as it could be. So if there's a perfect predictor, can I find that? Well, there's not usually a perfect predictor, but it's helpful to be able to look for one. And then there are other cases where, again, we're trying to find which predictor to use, which is the one that keeps the number of errors below some value. But that's always looking for one predictor. So how does SafePredict contrast with this previous work? So again, it's a meta algorithm. So there are a bunch of predictors below base predictors for an online setup, meaning we're getting data as we go. This online setup will not necessarily at all be independent and identically distributed, IID. It won't be necessarily. And it's going to guarantee that the error rate on the non-refused predictions is bounded by whatever the user specifies. And the guarantees are not going to depend on any assumption about the data or the base predictor, but are going to be asymptotic in the number of non-refused predictions. In other words, we could do quite badly for a little while. And the number of refusals and the percentage of refusals will depend on the quality of the base predictors. And if in fact the base predictors do well, meaning their error rate is lower than the one we're looking for, then we will refuse quite seldom. So looking at this pictorially, we have a predictors P, and we have some target rate. And what we would like to do is we'd like to, the meta algorithm will decide whether or not to accept the prediction from P. And we'll do that with some weight that depends basically on the history of how well the predictor has been doing. So just as you might ask your friend for a movie suggestion, if the friend's suggestions have been good in the past, you'll give a high weight to that. If the friend's suggestions have been very bad, then you might give much lower weight. So that's our basic scheme. And what we would like is we would like that the loss, which means when we accept a prediction and it's wrong, we want that loss for the accepted, for the non-refused predictions, divided by the number of non-refused predictions to be less than or equal to some epsilon, which is our target error rate. We don't want to exceed that target error rate. And that's what validity is. And efficiency says that we'd like the number of non-refused predictions to be very close to the number of predictions that the base predictors make. So that would be ideal. And what SafePredict achieves is that it's going to be valid for any base predictor, even if it's not very good, but then it might refuse a lot. And it's going to be efficient when P performs well, meaning when the base predictor already performs at below the epsilon error rate. So what we're going to do is we're going to combine a bunch of expert opinions to perform almost as well as the best expert. And we're going to use a scheme from Littlestone. And what this is going to do is it's going to give us a bunch of weights on each of the predictors. And we're going to follow the predictors with certain probability. And the fewer errors that the predictor has made in the past will make that weight of that predictor higher. And if one did this, so this is the Littlestone scheme, then one can get a loss that's very close to the minimum possible loss of one predictor based on this this ratio, this square root of t log n. But that's actually not so good because, well, I mean, just because this is a pretty big bound, basically, that's why it's not so good. And so we're gonna reformulate this a little bit, and we're gonna have, and when Anil used this figure, I thought it was so clever. So this crash dummy here, this dummy is going to simply refuse sometimes. So we're going to have the base predictors, and then we're going to have the dummy, and the dummy is just going to say, no, I'm just not going to predict. And if we just use the scheme from Littlestone as it is, then the difference between the actual losses for the non-refused predictions, the fraction of losses of the non-refused predictions could be this high, which would mean that t star has to grow quite fast. It has to grow faster than the square root of t for the right-hand side to be small. I mean, hopefully much faster for this to be small and for this ratio, therefore, to be near epsilon. And therefore, we're going to do a slightly different scheme whose details are in the paper, but the guarantee we give is that instead, the difference between the actual losses over the non-refused predictions for the fraction of non-refused predictions that are incorrect minus our target will be very close to 1 over square root of t star being the number of non-refused predictions. And so the whole point of that is that the more non-refused predictions we have, the closer we get to epsilon. So at the very beginning, we could be quite far from our target error rate of epsilon. We could be 25% if our epsilon is 10%, but fairly quickly we'll get to the point where, as long as we're not refusing too often, we will converge to that epsilon. And further, SafePredict is going to be efficient as long as the base predictors have an error rate less than epsilon. So this is the property we want. We don't want to be refusing all the time, because then it would just be trivial. And so we can also show that if in fact the error rate is low, then SafePredict will accept almost always. And so as we go to infinity, the number of refusals will be finite almost always. Now, so that's the basic idea of SafePredict, and the SafePredict as it stands does suffer from a little problem. And the problem, I mean, as I've presented it so far, suffers from the following problem. If, in fact, the error rate goes high and our target rate is much lower, let's say the error rate is really high, then what will happen is we'll start to refuse pretty quickly, and then we'll never, ever accept again. So if your friend gives you a bad movie recommendation, then you just say, well, I'm just never trusting you again. But maybe the friend kind of gets better at judging movies. So, it might not be such a good strategy. So instead of that, we use something called weight shifting, where even though we've been refusing because in this case, your friend has been giving you bad recommendations, you're going to sort of try it out. You're going to try out some of those recommendations. And eventually, because you've tried some out, your friend will get more credibility, and therefore you will start to trust those and you will refuse less often. And so weight shifting basically says, okay, the dummy, because of initial bad behavior on the part of the predictor, the dummy has all the weight, but what we're going to do is we're going to let the dummy shed some of its weights to the predictor from time to time, so that sometimes the predictor will be chosen. We'll try out those predictions. We won't do it too often if the predictor does badly, but if the predictor does well, then we will very quickly start to depend more on the predictor. So your friend's future recommendations might be heeded by you. This, we can make sure that this preserves the validity. So remember, the validity is that any non-refused prediction, the set of non-refused predictions should have the error rate that we're looking for, but it will make the probability of refusal go down. And that's why we get this curve, the kind of curve that we have here, where even though the base predictor went way beyond our target rate of 0.1 to 0.2, after it goes back to 0.1 or lower, eventually we stop refusing. That's because we've done some shifting to the predictor, and therefore we start to trust the predictor more. SafePredict is all it's doing is it's deciding when it's going to accept the prediction, and but we have other things that we can do that are meta algorithms that could feed SafePredict. For example, when the data is independent and identically distributed, this is IID, then very often what we could do is we could look at the current input, say, oh, wow, that was similar to some previous input for which I did well, and so I'm going to make a prediction. Now, SafePredict doesn't do that. SafePredict just looks at the results. It doesn't look at the similarity of one input X to another input X. But the confidence-based refusal mechanism is a great heuristic if the data is even approximately IID. And so a hybrid approach is to employ SafePredict on top of other refusal methods, giving us this kind of workflow. We have the base predictor here. We have a confidence-based predictor here, refusal mechanism that's going to be kind of with an underlying IID hypothesis. And then we have SafePredict. And what happens, though, is that if SafePredict gets all these predictions after this initial refusal mechanism, and they're still wrong, so your friend, is actually a collator of other people's advice about the movies, and and collates the advice, and swears by his or her sources, but yet the movies are bad. So SafePredict will say, okay, friend, you've got to get a new set of friends, a new set of sources. And so the analogous thing for us is that if the confidence-based refusal mechanism predicts, but SafePredict refuses a lot, then we're going to interpret this as that the IID assumption upon which the confidence-based refusal is based, it didn't work out so well. And so we really would like it to start over. We'd like it to get new friends, basically. And so we call this amnesic adaptation. So if some number, some threshold of the last 100 predictions have been refused, meaning SafePredict said, I don't really believe you, then you forget the history and reset the predictors. So you basically say to the predictors, hey, you've got to have new neural nets or new random forests or whatever. And then maybe then the CBR will have a better time of it, and then we will have a better time of it. So we have basic SafePredict that could refuse too often. We use weight shifting, so it refuses less often. We use CBR as a preliminary filter because that works really well for IID data. And then if the CBR output is not so good, then we use this amnesic approach to ask the base predictor to change either the base predictors to change, and maybe the CBR threshold mechanism to change. So here are some numerical experiments. And so again, what we always talk about is the error rate and the efficiency. And so we have MNIST, which I'm sure you're familiar with. And what we've done here is we've introduced a change point, which is where what used to be 1 becomes 4, and what used to be 5 becomes 2, or and basically the numbers, the identity, the labels on the numbers are just changed. We just artificially change them. And of course, what happens is that the initial random forest learns, and then when this change occurs, it's going to be predicting stuff, but it's going to be completely wrong. That's the blue here. The confidence-based refusal mechanism is the green, and that does great until here, when so that does even better than the random forest, because it might see a very fuzzy number and say, I don't want to predict that one, so it refuses properly. But then when the change point happens and labels have been shuffled around, then it doesn't do well at all, because it's still thinking everything is IID, and after the change point, after the change point and before, of course, things are not IID. And so then all of the other lines have to do with SafePredict, and the difference among them is their efficiency. In other words, how often do they not refuse? So we'd like to, the ideal thing would be we never refuse, but of course, that's not good either, because at the change point, actually, we should refuse. And so if we use the mechanism of just plain old SafePredict, then we'll tend to refuse quite a bit, and our efficiency will be low. If we use, however, amnesia, confidence-based refusal, and SafePredict, then we get this black line, and the black line is actually the best in the sense that it gives high efficiency while still meeting the error rate. So what that shows is that SafePredict with these added other methods can give can meet the error rate and still be reasonably efficient. And here's another classic data set of non-coding RNAs, and actually the graphs look remarkably similar. In fact, Anna and I had a discussion about whether they were the same, but they are not the same. They just look similar. But the conclusion is actually the same. So just to summarize, SafePredict works with any base algorithm or even an ensemble of algorithms, and asymptotically guarantees an upper bound on the error rate. The error has to be bounded, so it works for classification problems easily, like yes, no, but or several classes. And it works for numerical prediction where the possible values lie within a finite range. So if the possible values are like between 0 and 100%, then SafePredict could work. The error guarantees don't depend on any assumption on the data or the base prediction algorithm, but the refusal rate could go up if things are bad. And in changing environments, we have these schemes of weight shifting and amnesic adaptation, so that we might want to redo the base predictors or redo the confidence-based refusal, and also might want to give more weight to the predictors if we've been doing badly for a while, but we think maybe the predictors are doing better now. I would also like to point out that we have the code ready. I mean, the code is available to you, so you could use it. So if you had a pipeline and you have some machine learning, and then they make predictions, but the error rate is too high, you can incorporate SafePredict, especially if you're using scikit-learn. And if you're using something else, well, I think you'll see the architecture and you could be inspired. And then we would love to get your, if you do this, we'd love to get your version if it's on TensorFlow or whatever. Okay, so that's the first part. How are we doing on time? We're doing more or less okay. Anyway, the last part is going to be quick. I'm just going to do a couple of slides for each of these. So with a group at INRIA Montpellier, Titouan and Alexis, what we're looking at there is, it's not SafePredict exactly, but it's kind of inspired. There are many times when you have an algorithm that looks for top K. And top K is, because you don't want to say I can identify the correct class for sure. So instead, I'm going to identify, let's say, 5 classes and hope that the correct one is there. And what we are thinking is that maybe it's better that sometimes you could choose fewer than K labels if you're quite sure. You see a rose and you say, aha, that's a rose. And then there could be some other plant that you're really not sure about, and you would want more than 5 labels if K is 5. But what we want is we want there to be an average of K. And what we can show is that this average K notion is better than top K in the sense that it gives a lower overall error rate. And the reason for that is kind of intuitive, but I'll try to explain it this way. Let's say that there's some pictures. This is CFAR. Let's say there's some pictures and you say, okay, this is a horse, no problem. This is a deer, that's not a problem. Here we don't know whether this is a cat or a dog. Here we don't know whether this is a car or a truck. And here we're kind of confused about three classes. So the top 1 error rate might be this. We might ask for top 2, and that would cover these 2 cases. But what would be nice in the average K case is that we can say, well, here we're not going to ask for 2. We're just going to say it's whatever it is, a horse or a deer. And here we're going to say, aha, we really don't know. We think it's one of these 3 things. And so intuitively, it should make sense that we shouldn't always ask for exactly K. If we're looking for an average of K, we should look sometimes for fewer and sometimes for more. And that's what we find. What we find is that in cases where, so there's something called ImageNet, and in cases where we're looking for K equals 5, top K has a certain error rate. Let's say top 5 has a certain error rate in the orange, and average K has what you see in the blue, and so the average error rate is lower. And so yeah, it works. It also is nice because you can use totally classical machine learning algorithms as the input. And in some sense, this is another meta algorithm that just says, should we use top K or average K, and using average K is better. Okay, and then with Ben, Per Herr Stoffer, I always have trouble. I don't usually have trouble with German names, but this one I do. But it's all right. He says that other people in Austria also do. So you consider a complicated engineering system with many possible input conditions, and there might be parameters that affect the output. And we want to do, there are actually several things we can do with what I'm going to discuss with you. But one thing is sensitivity analysis. We want to say which parameters are important. But here, what we're thinking is it's expensive to evaluate an input condition. Maybe we have to do an actual physical experiment, or maybe the model is just very, very complicated. And so what we want to do is we want to sample strategically, and so only do those expensive experiments rarely. And basically, that's our contribution. It's a better estimator that selects samples better, and therefore can give better results, give a more accurate result. And so here's an example. There's a beam, it's clamped to the wall on one side, and then a vertical force is applied to the free end. And the stiffness and the material properties vary along the length of the beam in some way that we know, but we don't know exactly. I mean, it's quite complicated. And so the truth model is a finite element model with tens of thousands of degrees of freedom. It's really expensive to evaluate. So what we'd like to do is we'd like to apply the truth model for only a few forces, few input forces, and try to get a good estimate of the sensitivity to various parts of the materials. And so our estimator approach can do that. It can give a lower MSE, mean squared error, than the state-of-the-art algorithms. And so what we're trying to show here is that, of course, as you test more, your error goes down. So if you do more of these calculations, the error goes down, but also by using this method, you can test more, but test better. Okay, that's it.
Awesome. Thank you so much, Dennis. We got a bunch of questions, both from the students we have in the CS 528 class that's watching, as well as on YouTube. So I think just to kick us off, and also just a reminder to folks on YouTube, you can keep posting questions in chat and we'll keep track of them. I guess just to kick us off, I'm curious about the relationship of SafePredict to things in bandits, and specifically if there are things like the setting that you talked about, this online setting. I'm wondering if you've thought about other settings, such as a BAT setting where maybe you have historical data about each of the base predictors and you get to observe some information about how they behave. And then you talked about this cold start problem for the meta predictor, right? Like in the beginning, there's a little bit of time that it takes to adapt. And I wonder if there's, for real use cases, maybe where there is historical data, that might be actually a useful way to alleviate some of those issues. So I'm wondering if you've thought about that, or if there are other extensions that might be useful there.
Well, let me answer, and then Anil, if you have more to say, then by all means. So the confidence-based refusal mechanism could use such historical data for sure. So if you know that certain predictors have done well, then you could use a confidence-based refusal mechanism, and it will say, I really like that predictor. It's been doing great. My data is probably IID more or less, and so I'm going to weight that predictor more than this other predictor. And so you'll get this kind of overall prediction. And if the confidence-based refusal mechanism says, I don't believe it, it's just too vague, I really am not sure what classification, well, then SafePredict is not going to have to do anything. It's only if the confidence-based refusal mechanism says, I believe this, then SafePredict will say, okay. And if in fact CBR is doing great, then SafePredict will just say, oh, well, I trust you. And so it's going to not refuse. So there won't be so much of a cold start problem.
I see. Sorry, Mustafa, do you have anything to add there?
Sure. I mean, the relationship to existing expert algorithms, expert advice algorithms is obvious. We don't really invent a new algorithm. It's more like we use existing algorithms in I'm hesitant to say smart, but at least a convenient way to introduce a method that is easy to implement, easy to interpret, and easy to use. In particular, that weight shifting is fixture algorithm. Basically all math is following up through the same methods in the original paper, Warmuth paper. And in terms of if you have some priors from before, basically as Professor Shasha mentioned, you can bake it into the base predictor, or you can. We are basically starting with an initial weight for the base for the dummy or the base predictor. If we don't try, if we are confident that our base predictor is gonna do well, we can give a smaller weight to the dummy. And it's not that crucial in our experience because the weights, especially if the base predictor consistently doing well or bad, is exponentially converging to either not zero, alpha in the weight shifting version or one. So that parameter is not even that crucial as long as the horizon we are considering, the t is not too small. I'm not sure if I give a too indirect of an answer, but
no, I think that makes. I think I follow the intuition for sure. Yeah.
I was wondering if you could speak a little bit about the types of applications that SafePredict has maybe been deployed on, or that you're thinking of deploying it on. I think we got a question from the class, like in what kind of settings would you expect the base predictor rate to change like that? And Mustafa, I know that you're at the Broad Institute now, so I was wondering, are they using it, or using it there, or using like similar SafePredict type algorithms? I know this was your thesis a little while ago, but I was wondering what is the current state of things? Are you using it these days? Me myself is not much because for the last three and a half years, I'm learning more biology and trying to adapt to this new untrustable face of the data. It's a humbling experience, both learning the biology and trying to navigate in the scarce data regimes. So online settings is not really working well in at least the line of work that I'm focusing on. But as an example where SafePredict could be used, maybe one can consider forecasting, investing algorithm situations where you have a baseline, say the non-risky investment instrument, and its income or its return can be considered as the dummy's loss or reward. And you can compete with that. It can be your dummy. Maybe Professor Shasha may have a better example.
No, I mean, that's a great example. So the dummy would be just putting the money in the bank, which has been a dumb thing to do for a little while, but might not be in the future. And then another example where there are change points, which I think also is part of your question, are things like recommender systems. I mean, and it would be if somebody asked you for a movie recommendation and you said Gladiator, well, I mean, it's a great movie, but it's not probably the movie recommendation that a person might want now. So things change. So things aren't IID, and so it is in a way recommendation systems are in a way a forecasting system because they're saying what you will like, but they in fact what you will like could easily change in time and therefore is not IID.
Right. Yeah. That's a really good point. Curious about when it will tell me to invest in Bitcoin.
Yes. I mean, markets are really hard. They're really hard. But there may be things that where either the market is not so developed or or something. I mean, another area that we would like to do, but we don't really have the expertise is medical diagnosis of an evolving of a patient evolving in unfortunately in sickness. So there in a way patients are IID in some sense because you see the same conditions, it's the same same result, but it's not really true because depending on the trajectory of the patient's illness, things might not at all be IID. And so, so that would be another area where I think it could be worthwhile. Let me tell you an area where it would not be worthwhile. Okay, you would not want to use this for driving cars, right? Because you're just not, you don't have the luxury of refusing a prediction. Right? You just can't say, well, I'm sorry, I'm just going to ignore that because, you know, what do? Just go straight? So that would not be good.
Well, refusing in that scenario might be just waking up the actual driver.
Okay, fine. Good luck with that. But yeah, that's true. That would be good.
It's actually, your example of like recommender system applications made me think of the potential use of this as a mechanism for like human in the loop / active learning kind of scenarios where I can imagine maybe the data that is refused for prediction is, you know, it's likely going to be the one that could be particularly beneficial for either labeling or relabeling or something like that. Do you have any comment about it? What do you think?
Yeah, no, I mean, actually, I completely agree with that. I mean, that's why I brought up the Kahneman example from before, at the beginning, that that there could easily be cases where, you know, let's say we've been doing predictions and it hasn't been good at all. So then maybe we definitely do want to bring the human in the loop. You know, just the conditions are so weird compared to anything that the machine learning has been trained on, that really it's just unprecedented. We don't know what to do.
I think we have more questions from you know, the audience as well. So I'm just going to go over some of those. I think one question which asks a little bit about the feedback mechanism that you know, the meta predictor has. So I guess in this setting, you're kind of revealed at each time step, the loss is revealed to the base predictor. So are there other like settings where, you know, maybe the mechanism with which you get feedback is delayed or somehow, you know, not immediately available? And how does that relate to, let's say, applications to, let's say, real-time settings where, you know, you don't often know what the loss might be instantaneously?
Arnold, you want to do that one?
I mean, I would say that's the natural extension. And if I was doing PhD one more year, maybe I would be working on that. But I mean, as usual, in the classical delayed feedback setup, as the guarantees get looser, but still there, I think we would be able to get similar things by adapting those algorithms, including dummies in the sense that whatever we want to guarantee, and there would be a trade-off how ambitious we are about our guarantees versus versus the fidelity of the feedback. But do we have any existing work on it? No. Am I aware of any? Not really, but I might build a bit up to date, to be honest.
Yeah, but it's a cool problem. Yeah, for sure.
I thought we got an interesting question in the YouTube live chat about, is there a parallel to kind of reinforcement learning based techniques? Because you kind of have a scenario of maybe some explore and exploit where you kind of need to think about, should I listen to my friend's recommendations again? Hasn't been long enough to like maybe, Avengers movie number 7 will actually be okay for me. Do you ever think about it in those terms? Is there like anything from the RL literature that you can take and kind of adapt to your setting like that?
I'm gonna ask Arnold to answer that one too, please.
In terms of application, it seems very relevant. Unfortunately, I don't trust my expertise on around reinforcement learning literature to be able to say something meaningful. But there is at least this. I mean, the same connection between any expert advice setup to reinforcement learning algorithms naturally transfers to in our setup too. Do I have anything more concrete? No, unfortunately.
Yeah, I mean, really, this architecture is pretty similar, as the questioner notes, to a reinforcement learning setting.
Yes, but I guess going back to Karen's question, if we choose to not predict, what is the reinforcement we are getting? If there is no feedback in those cases, then the problem, at least the nature of the problem, changes significantly.
Right. I think we also had a couple questions both from the class and from the audience. Does SafePredict kind of need to know the error rate of the underlying predictor? And in practical applications, kind of how do you get that? Is it provided by end users? And if you don't need that, or if you don't have that, how does the algorithm change?
So SafePredict doesn't need to know that. That's the hope. That's one of the beauties of it. But it does, I mean, as presented today, it does need an instant feedback as to whether the prediction was correct or not.
Yeah, I guess the question is...
That would be terrible if it had to know the error rate, because that's actually what Chow did in 1970. He said, if you knew the conditional error rate, then it's easy to figure out whether to accept or not. If the conditional error, if the probability of being correct is high enough, then you accept, and if it's not, then you don't. So yeah, no, gotcha. We don't have to know that. We don't have to know that at all.
I guess then the question is, if you need to know whether the prediction was correct or not, how do you kind of get that information in a real world setting?
Well, I mean, let's say you go to the movie and you don't like it, so you know that way. Right. Or you buy the stock and sell it tomorrow and you lose money, and then it's, gotcha. You know it.
I think in many scenarios where there's user behavior, you can then observe immediately after that user behavior in general, right?
Yeah.
I think there's a set of questions which I think are related to this idea of layering these meta algorithms, which I think is an interesting kind of extension that you presented as well, like having CBR in the middle and then having SafePredict on top. And I think there are some technical questions here. I think in our class, somebody was curious about how the CBR mechanism works and maybe talking a little bit through that. But at a high level, I'm curious, like, how this kind of mechanism layering idea, like, to what degree can you kind of take that? Is there possible to like do multiple layers, like maybe 3 layers of these, gates, essentially, and how does that work really, like, conceptually?
Well, let me try it, and then Anil, you add maybe. So in fact, right here, there's actually an implicitly 4th gate, which is that P may not be a single predictor. It could be a set of predictors. So already we have an ensemble there. And then the CBR typically, let's say that P is just one predictor, just to be simple. And let's say it's a random forest, just to be very concrete. And let's say we're doing a classification problem. And let's say that 70% of the trees in the random forest vote for yes, and 30% vote for no. If there's several labels, 70% vote for label L, and the others vote for other labels. We would have, the CBR might have some threshold that says, if it's over 72%, then pass it on. If it's not, then don't pass it on. So that's a typical way that a confidence-based refusal would work. There's always some score that you get from a base predictor, and it might either be the base predictor itself or the result of the ensemble, but you use that score as the input to CBR, and then if that score is above a threshold that based on the past, that threshold is high enough, then you say, okay, CBR says, go ahead, make this prediction. SafePredict could still say no, but at least CBR says yes.
I see.
An interesting segue on this, which is actually something that someone asked in the chat too, which is what's the relationship with the calibration of the models and of the predictors. My understanding is, for instance, that SafePredict it can be a mechanism for also compensating for a relatively poorly calibrated model, but with with CBR wouldn't have that luxury. But I'm curious to hear what your take is on this.
Well, no, actually, we're quite, we quite love ongoing calibration. If the base predictors, are use stochastic gradient descent or something, and they're constantly getting updated, that's fine. We love that, because all that's going to do is it's going to make things better. And similarly, for the confidence-based refusal, if its thresholding or the weights that it gives to inputs are changes, then it can adapt too. So basically, any underlying adaptive algorithm should continue to do its adaptive job. The feedback that you're seeing here in blue is just saying, hey, look, we don't know how you've been doing, all your adaptation. It's not really been working for us. So please, start over, basically. So, become amnesic and start over.
Yeah, it makes a lot of sense. Thank you for that.
One of the things I was wondering about kind of throughout the presentation was, in a lot of settings, some errors can be kind of more expensive than others. Like if you have a COVID test, for example, a false negative COVID test is in some sense, well, depending on your perspective, like might be more harmful than a false positive. Is there any way to, or have you thought at all about adapting SafePredict to those situations where, there might be some cases where you want to be a little overzealous in your rejections, or other cases where you might not want to reject as much?
I mean, it goes in the loss function. So the loss function could be different for the different kinds of errors.
Gotcha.
Yeah, I think by just baking that into loss function, that will be sufficient in most scenarios. And that would also give, as long as you want to control one of those errors tightly, you can give an upper bound in terms of the epsilon. You can choose your epsilon according to, say, you always say positive, what's the loss you will suffer, and you can decide your epsilon, set your epsilon to that, basically.
Would a similar approach work for, let's say, so I was also curious about one thing, which was like, I think last few years, there's been a lot of work on like robust machine learning, specifically when you have one predictor, but it has, differentiated performance across parts of the population. Like it's much worse on some parts of the population than others. And I wonder if that's another kind of case where you could wrap it in this meta algorithm and then decide if you shouldn't predict if you get a prediction for a part of the population where things are generally worse for the base predictor versus other parts where it's better.
Well, for the population, it would require a little bit massaging to the algorithm, since it's not one by one. But I would say that is kind of a good example where CBR or some base predictor, some base keeper would be particularly useful, because if you look at SafePredict, how it works, it only takes the loss functions or the errors or losses and assign assign the weight for the dummy. That's all it does. But to be able to detect populations which respond differently or distinctly from the rest of the population, you need to be able to infer the conditional distribution of the response and the population characteristics, whatever we are measuring, say age, sex, weight, whatever. And all those assumptions about either both priors and assumptions about that conditional distribution can be baked into the CBR or the base predictor, which would decide accordingly. That's maybe going back to your previous question. When adding a CBR would be helpful, when we believe that we know some background information, or we can learn something about the conditional distribution between X and Y, rather than just Y and Y hat.
Right. I see. I think we're very close to time, so I just want to throw in a couple of maybe lighter questions about, I think me and Dan were talking about this. We couldn't help but notice that, Dennis, you have written a bunch of puzzle books and so on. So I'm curious if you have another book on the way, or if you can talk about, your interest in puzzles and how that came about.
Well, sure, thanks. Yeah, so I write the puzzle column for CACM. And what I really like about puzzles is that I formulate the puzzle and then I realize that a slight variant of that puzzle I can't solve. So that happens a lot. So the column is called Upstart Puzzles, and so the way it goes is I explain, some problem, I explain some simple examples, give some solutions, and then I say, now here are problems that I don't know how to solve. So I've used puzzles throughout my career as ways of trying to find a simple conceptual way of understanding a bigger problem. So when I worked for IBM, which was an important company when I graduated from college, it's still important, but maybe not as important. Anyway, it's a wonderful place to work. And one of the problems was to design circuitry that would stop the computer if there were an error within 2 cycles. And so I thought of that. And the reason this was important was that if the circuits sometimes would not fail in a hard way, meaning once there was a failure, it would always be there. They would fail kind of just occasionally. So a circuit that fails occasionally is something like a liar that lies sometimes, but not always. And so some of my early puzzles were just to help me design those circuits. So I was basically thinking of puzzles where there were occasional liars, not permanent liars, just occasional liars. And what do you do with that? And how do you solve that? So it's been a good heuristic for me just to formulate things that seem very technical into their essence as a puzzle.
That's super fascinating. Thank you for sharing.
Very cool. Yeah. Okay, I think for the YouTube audience, we're at time. So I would like to thank, our speakers and everybody who tuned in on YouTube. Thanks for tuning in. And go to our website, mlsys.stanford.edu, if you want to check out our schedule or join the mailing list. We send out weekly reminders for talks. Subscribe to the YouTube channel, like the video, and see you all on YouTube next week. But we're still going to continue for folks in the class. So bye to YouTube.